Okay, for centuries, a really simple question stumped some of the greatest minds out there. You roll a ball and it stops. Why? I mean, why doesn't it just keep going? Well, the answer to that little question ended up revealing a set of rules that govern, well, pretty much everything, from that rolling ball to the planets whizzing through the sky. So today we're going to unpack Isaac Newton's 3 incredible laws of motion.
So let's really start there, with that ancient question. You give a ball a good push, right? It rolls for a bit, but it always, inevitably slows down and stops. So why? What is actually causing its motion to just end?
Well, for a really long time, what seemed like the common sense answer was that, objects just prefer to be still. The big idea was that rest is the natural state for everything. Motion, that was seen as this temporary, forced thing that needed a constant push to keep it going. But as it turns out, that's not quite the whole story.
Right, so the person who really started to pull at this thread and unraveled a whole mystery was none other than Galileo Galilei. He came up with this completely new way of thinking about motion. And the trick was, he didn't just look at what was there, he started imagining what would happen if something wasn't.
He came up with this brilliant thought experiment. Just picture this. He noticed that when a marble rolls down a ramp, it speeds up. Makes sense. When it rolls up another one, it slows down. Obvious, right? So then he asked the big question, what if the surface was perfectly flat and perfectly smooth? With absolutely nothing to slow it down or speed it up, the marble would just keep going, forever.
And that right there, that thought experiment, it perfectly points to the real reason things stop. It's not because they want to. Nope. It's because of this hidden, ever-present force that's always working against motion in our world. Friction. It's the friction between the ball and the ground and even the air it pushes through that are the real culprits bringing things to a stop.
Okay, so this leads us to a really crucial idea. Imagine you're pushing a heavy box. If the force of friction pushes back with the exact same strength you're pushing with, well, those forces are balanced, and that box isn't going anywhere. To get it to move, your push has to be stronger than the friction. You need what's called an unbalanced force to change its motion. And believe it or not, this simple concept is the very foundation for Newton's first law.
So this is where the man himself, Isaac Newton, steps in. He took Galileo's amazing, groundbreaking ideas and basically formalized them, turning them into his first law of motion. You probably know it as the law of inertia. And it's all about how stubborn objects can be, how they resist change.
So what exactly is inertia? Honestly, in a nutshell, it's just stubbornness. It's that built-in property that makes an object that's sitting still want to stay still, and it makes an object that's already moving want to keep moving in a straight line at the same speed. It just wants to keep doing whatever it's already doing.
And you feel this constantly, every single day. Think about it. When your car slams on the brakes, the car stops, but your body's inertia wants to keep going forward. That's why you lurch against the seatbelt. Same thing on a bus. When it suddenly takes off, your body's inertia makes it want to stay put, and that's why you feel like you're being thrown backward. But that raises a good question, right? Do all objects have the same amount of this stubbornness? I mean, is it just as easy to change the motion of a little tennis ball as it is a heavy bowling ball? Probably not.
We all know this from experience. It's way easier to push an empty cardboard box across the floor than one that's packed with heavy books. That box of books, it just puts up more of a fight. It has a much greater tendency to just stay put. In other words, it has more inertia.
And here's the crucial point. This resistance to change, this inertia, it can actually be measured, and the measurement we use for it is mass. It's that simple. The more mass an object has, the more inertia it has, and that means it's harder to get it moving, harder to stop it, and harder to change its direction. Okay, so we've established that you need an unbalanced force to overcome inertia. But what happens then? When you do push it, how much does its motion actually change? Well, that is where Newton's incredibly powerful second law comes in. So, in his own words, Newton's second law is a bit formal. But what it really boils down to is this. An object's acceleration is directly linked to how much force you apply to it. So if you push something gently, it speeds up slowly. If you push it hard, it speeds up quickly. It just makes sense, right? And this law gives us the exact formula to figure out that relationship.
And here it is, one of the most famous equations in all of physics. Force equals mass times acceleration, or F equals ma. It's beautiful in its simplicity. The harder you push, that's more force, the faster it accelerates. And the heavier it is, more mass, the less it accelerates for that very same push.
And what's really cool is how this law explains techniques we see in sports all the time, even if we don't realize we're looking at physics in action.
Okay, so when a fielder catches a super fast-moving cricket ball, they instinctively pull their hands back as they catch it. But why? Well, the ball has to go from really fast to zero. By pulling their hands back, they increase the amount of time it takes for the ball to stop. And if you spread out that stop over a longer time, you reduce the ball's acceleration. And according to our friend F equals ma, if you reduce the acceleration, you dramatically reduce the force. Less force means less sting on the hands. Pretty smart, huh?
All right, so we've covered inertia, and we've covered F equals ma. Now Newton's third and final law reveals this really simple but profound truth about forces themselves. They never, ever exist all by themselves.
I'm sure you've heard this line before, but what does it really mean? It means that anytime one object pushes or pulls on a second object, that second object is, at the very same instant, pushing or pulling back on the first one with an equal and opposite force. Every single time. No exceptions.
Let's take something as simple as walking. To move forward, you have to do something first, right? The action part of this is your foot pushing backward on the ground. And here's the kind of magical part. The reaction is the ground pushing forward on your foot with that exact same amount of force. Just think about that for a second. It's not really your legs pushing your body forward, it's the reaction force from the entire planet pushing you forward that actually gets you moving. Wow. And once you see this action-reaction principle, you see it absolutely everywhere. A rocket pushes hot gas down, and that gas pushes the rocket up into space. A rifle pushes a bullet forward, and the bullet pushes the rifle back into your shoulder. That's recoil. The forces are always there, always in pairs, and always equal and opposite. So there you have it. Those are the three laws that are the absolute bedrock of classical mechanics. Let's recap real quick. First, an object's motion won't change unless an unbalanced force acts on it. Second, we can calculate that change precisely with F equals ma. And third, every single force is just one half of an equal and opposite pair. You know, these laws aren't just some dry equations in a textbook. They are literally the invisible architecture of our physical world. From the way your body leans when you take a sharp turn in a car, to launching a massive satellite into orbit, it's all governed by these same three elegant rules. So the real question is, now that you know them, where are you going to see them in action next?